Okay, so we're going to begin our set looking at this set called the integers. These are just the whole numbers, 0, plus or minus 1, plus or minus 2. We denote it by z, by that the symbol z, a boldface type z. And we say that an important relationship is divisibility. We say that for two integers, a divides the integer a divides the integer b, if there's some other integer s, where b is a times s. So we might denote that by a slash b, where a divides b. An equivalent way of saying a divides b is saying that a is a divisor of b. And one very axiom, a fundamental axiom of the integers is the well-ordering principle. That says every non-empty set of positive integers has a smallest element. Again, this does not apply to all the integers, as evidenced by if you look at all the integers, there is no smallest integer. But there is a smallest positive integer, 1. 1 is the smallest positive integer. And an important consequence of this well-ordering principle is the division algorithm. So we'll move this camera to the board here. And we'll see how far I can go over here. And so perhaps that's best to draw a line here. Okay, so a theorem that is proved from this is the division algorithm. If a and b are two integers with b greater than 0, then there exists unique integers with we should give these integers name. Let's call them Q and R. Where A is Q times B plus R, and R is less than or equal to 0 and strictly less than B. So R is called the remainder and Q is called the quotient. And the unique means there are no other pair of integers with these properties that satisfy this equation. So let's prove this using the well-ordering principle. But not directly. Let's first consider a case. So to begin our proof, suppose A divides B. Suppose B divides A. Then there's some integer q with B, with A equals Q times B plus 0. So the result holds. Where Q is given by the fact that B divides A, guarantees the existence of such a Q, and then the R would just be 0. Okay, so we've handled that case. If B does not divide A, we look at the set S of A minus NB, where N is in Z, and A minus NB is strictly greater than 0. Which, since A minus NB is an integer, that really means A minus NB is greater than or equal to 1. So we want to try to apply the well-ordering principle to S. So to do that, we need to show it's non-empty. So if A is greater than 0, A minus 0 times B would be an element of S. And so S is non-empty in that case. A cannot equal 0 since anything divides 0. So B would divide A in that case. So what's left? If A is equal to greater than 0, S is not empty. If A equals 0, that can't happen. What about if A is a negative number? Then it turns out, if you look at A minus 2AB, which is equal to A minus 1 minus 2B, and that would be an element of S. Y, well, certainly fits the form of this type. But since B has to be strictly greater than 0, in other words, B is greater than or equal to 1, 1 minus 2B is going to be a negative number. So this would be negative. And then by assumption, A is negative, so we would have two negative numbers, two strictly negative integers multiplied together. Their product has to be positive. And so we can conclude then that S is not empty. And so it's a non-empty set of positive integers. It contains a least element. That's by the well-ordering principle. Let's see if we can get this just right. Probably as good as it's going to get. So, since this element, being the least element of the set, is a member of the set, there exists a Q with R equals A minus QB, or A equals QB plus R, by arranging things over. Also, R has to be greater than 0, because that's what the elements of S are, greater than 0. So, in particular, R has to be greater than or equal to 0. So we've got one of the inequalities. Why does it have to be less than B? So suppose that R was not strictly less than B, that R was less than or equal to B. Then that would give us R minus B as positive. If you look at R minus B, R is A minus QB minus B here. This ends up being A minus Q plus 1 times B. So what do we know? We also have, since B is positive, R minus B is strictly less than R. But yet, R minus B is in the form A minus an integer times B. So it looks like we may have a contradiction that R minus B would be smaller than the least element. So that's a contradiction. And then that proves that R has to be strictly greater than B. Again, we could note that if R minus B is equal to 0, that says that R would equal to B. So we have A equals QB plus B, which would be Q plus 1 times B, and that would mean B divides A. Which is not the case. Right? Remember, we've handled when B divides A separately, we've gotten our conclusion. So this proof that we're doing here is just in the case when B does not divide A. Okay, so we'll move on then, and it can also be shown that these integers are unique. So we prove the existence part of this statement. This involves not just there are two integers, but those are the only two possible integers. So let's try to prove uniqueness. So again, just going over what's written on that board, really the assumption, when we suppose that R is greater than or equal to B, since this is a proof in the case where B does not divide A, that suppose R greater than or equal to B really is equivalent in this case as saying suppose R is strictly greater than B. And we need that because in order for R minus B to be an element of S, we need that R minus B to be strictly positive. Okay, so to prove the uniqueness, suppose A equals QB plus R and A equals Q prime B plus R prime, where all those four elements are integers. And let me move over to the board. May even be able to write past here. Okay, so that's how we would start off here. Suppose A equals BR, and we have those four elements there, and then the end part would be course, that the two remainders are greater than or equal to 0 and less than b. Both r and r prime. And so, we can assume that r is greater than or equal to r prime. And actually in the notes I just showed the other case. The proof is similar. You essentially have an identical proof, just switching the prime and the non-prime one. Okay, so what we have is 0 is greater than or equal to r minus r prime. Which is less than or equal to r, which is strictly less than b. But if we look at r minus r prime, solving both those two equations, the a term would cancel, and we'd just be left with qb minus q prime b, or q minus q prime b. Again, that's subtracting this expression minus this expression. So what does this tell us? Well, this is less than b, but yet we have it's equal to an integer times b. So the only way something could be, a positive number could be equal, or something greater than or equal to 0 could be this number, to be a multiple of this number, would be if you would, that multiple was 0. So again, this implies that q minus q prime is equal to 0. Again, we have a number greater than or equal to 0 is equal to some integer times a positive number that is bigger than this. That can't happen. Think of it with just, how can a number greater than or equal to 0 be something but less than 5 be something times 5? The only way that could happen would be if it was 0 times 5. So once we have this which then leads to, if this is 0, r minus r prime would have to be 0. And so we proved uniqueness. So this concludes the proof of the division algorithm. So we'll move on now and introduce the concept of greatest common divisor. And we're going to define it actually a slightly different way. We're going to define it as an element that's created by the well-ordering principle. But then we will show the properties, it has the properties that you need in the greatest common divisor. So what are those properties? I'll put them here for future reference. One is that D divides A and D divides B. And the second is for any integer k with k divides A and k divides B, then k has to divide this element D. So if you define, one way to define the greatest common divisor of two numbers A and B would be that way. We're going to define it a slightly different way, using the well-ordering principle. So let S be all A M plus Bn let me actually get a setup first. Let's take two integers, not both 0. Let S be the set of positive integers of AM plus Bn, where M and N are arbitrary integers. S is not empty because A squared plus B squared is an element of S. You take M equals A, N equals B, so A times A plus B times B is in that form. And since A and B are not both 0, at least one of A squared plus B squared will be positive. The other one will be either positive or 0, so their sum is going to be positive. So S has a least element, call it D. By definition, that's the way I'm going to choose to define it. By definition, we define the greatest common divisor of A and B to be this least element. And now this really becomes like a theorem, if you will. where 1 and 2 hold, where D is defined as above, where D is defined to be the least element in the set of positive integers of this set here. And so we're going to prove this using the division algorithm. Okay, so let's try to prove this. Let D be the least element of the set S. So the set S is defined as all positive integers of that set A times A multiplied an integer times A plus an integer times B. And we're not going to look at that whole set, we're only looking at the positive elements in that set. That's what we call S. And so as we saw up there, up above, S is not empty, A squared plus A times A plus B times B is in it. So such a D exists by the well-ordering principle. So by the division algorithm, there exists Q and R with B equals Q times D plus R, where Q and R are integers and R is between greater than or equal to 0 and strictly less than D. So we like to show that one of these conditions, that the greatest common divisor of A and B divides B, we really like to show that's equivalent to showing that R is 0. B is just Q times D plus 0. Simply, B is a multiple of D. So to do that, we're going to show if R is not 0, we're going to get a contradiction. And you can maybe think about this, what might that contradiction be? It might be that this element D, this element R ends up being in S and smaller than the least positive integer. Okay, well what do we have? We can eventually see after some QB minus QD, but then D is equal to MA plus NB for integers in S. Again, that's because D is an element of that set, S. So no, that M and N, they have to be such integers, M and N. They may not be in S, I misspoke there. But there are integers that make, because D is in S, there are integers M and N that give us that equality. But after some juggling around, this would be negative QM times A plus 1 minus N times B. This is a multiple of A, an integer multiple of A plus an integer multiple of B. So that could be in the set S if, in fact, this multiple was positive. So what do we have? We have, but R cannot be, or maybe we should say we cannot have R greater than 0. Because if we did, then R would equal 0, then R would be an S. And it would be strictly smaller than the smallest element of S. This cannot happen since D is the smallest element of S. So R equals 0, which basically means a 0 remainder in this equation from the division algorithm means D divides B. A similar argument will show D divides A as well. So we proved the first thing of the theorem, this strange element that we took as a least element of the set of positive integers of this type, D, does divide the two elements A and B. So it is a common divisor. What would make it the greatest common divisor? So that is what we'll show next. So, to prove 2, we suppose K and Z is an integer, and K divides A, and K divides B. So that means there are two integers, s and t, with, since k divides a equals s times k. And since k divides b equals t times k. We also have, remember that d equals ma plus nb, which is m times tk, m times sk plus n times tk. So we end up with m n times s plus n times t all times k. Well, what does that mean? That means d is equal to an integer times k. So k is equal, k divides d as required. And we've completed the division algorithm. And now we can actually apply the division algorithm to find the greatest common divisor. So what we want to do is we want to sort of start with how to find the GCD of A and B. GCD, that is notation for the greatest common divisor. How do we find the greatest common divisor of A and B? What we do is we say let's just assume, let's call the bigger one A. It doesn't matter what we call A, what we call B. Let's assume the bigger one is B. So we get A equals as some Q1B plus some remainder R1. But then we can find R1 is basically B is equal to Q2 times R1 plus R2. With R2 less than R1. And we can keep going and going. These remainders get smaller and smaller. So at each point we sort of have Ri well, the next step, let me just explicitly say what would the next step be. The next step we'd say R2 R1 is equal to Q R2 maybe call this Q, just plain old Q, call this Q1, I think is the notation I'd be in. So you get R1 is Q2 R2 plus some remainder R3, where R3 is less than R2. So the remainders are positive numbers that are positive or zero that keep getting smaller and smaller and smaller. Eventually they must get zero. So eventually you end up with well, at each step, Ri is less than, Ri plus 1 is less than Ri. Eventually, we must get Rn is equal to 0, or let's maybe make it Rn plus 1 is equal to 0 for the first time, where Rn is not 0. Then the greatest common divisor is the last remainder in this process, the last non-zero remainder. So let us start with an example. And again, if you look through, some of these are highlighted in the PowerPoint slides, and I have, I believe, an example that I posted on the PowerPoint slide. So let's look at that. So we want to find the greatest common divisor of 30,051 and 17,019. Okay, so let me adjust the camera back. Okay, that's just about perfect. Move back just a little bit. I think the only word missing here is just the general, this should be fine. So let's begin to apply this on this board. So again, this is just what I talked about earlier of the second part of the proof. And then a little bit of how to find this. So we start 17,000 and change goes into 30,000 one time. With a remainder of 12,137. Now we divide this remainder into this. So 12,000 and change goes into 17,000 and change, again, one time. And now, let me make sure I have that remainder. Not quite, so we'll maybe move it over just slightly. That should take care of it. And here our remainder would be 5,777. Then again, we play this game again. 12,137. We divide 5,770. That actually goes in twice. With a remainder of 583. Then we'll continue on. We'll divide 583 into 583 into 5,777. That goes in a lot. I think it actually goes in 9 times. And again, the remainder on that would be 530. Then we'll go back into divide 530 into, something's wrong here. Oh, this is, this number right here. 5,777 is 9 times 583 plus 530. And then 583 is actually 1 times 530 plus 53. And then finally, 530 is 10 times 53 plus 0. So this is your last non-zero number. So the GCD of 30,051 and 17,914 is 53. And so that is the way to find it's called the Euclidean algorithm. It's a way to find the greatest common divisor, not by factoring the number and looking at common factors, but in looking at, repeatedly applying the Euclidean algorithm. Your remainders get smaller and smaller and smaller. Since the remainders always get smaller but remain greater than or equal to 0, eventually there has to be a remainder that's 0. The last non-zero remainder is the greatest common divisor. Another thing we can do is, well, can we express 53 as a greatest common divisor? And so we'll attempt to do that. Okay, so I'll move the camera in a second. What I've just put on the board there is express the greatest common divisor, so 53 as a number times 30,051 plus a second number times 17,914. 914. So let's see how we can do this. We're really going to use on our previous board those equations. So let me actually write them off to the side here. So we start with this 53. So from that last equation, 583 plus equals 1 times 530 plus 53, we solve for 53. So 53 is equal to 583 plus a negative 1 times 530. Bringing that over to the other side. Then I'll go the next line up, and what I'll substitute in, I have an expression for 530. So 530 is going to be 5,777 minus or plus a negative 9 times 583. Which, if I combine like terms, I have negative 9 of these, but that's with a negative sign, so that becomes a positive 9 of them, plus one more, so I have 10 times 583 minus, plus negative 1, or just minus. I like to keep the constant separate, so I'll say plus negative 1 of 577. And there's a chance you may make a mistake as you work through this, so each time it's good, each step after you simplify and gather terms must equal 53. So we should check that, and I did when I worked this out. Then we play the same game. Now we can get this 583 out of there, right? So what is 583? So we have 10 from over there times 583, but 583 was 12,137 minus 2, or plus a negative 2 times 5,777. And then we still have a negative 1 of these. So when we distribute through the sign, we'll have 10 of these 12,137. And then this will be a negative 2 times 10 is a negative 20. With the non-negative 1 would give us negative 21. So plus negative 21 times 5,777. Now let me go over to the computer screen and make sure this is picking this up. And it is. Now we go back, play the same game again. Let's get the 1237 and get rid of that. So this is equal to 10 times, I'm sorry, we get rid of the small one first. Getting ahead of myself. Let's get rid of this negative 21, 5,777. We can replace that by 17,914 plus a negative 1 times 12,137. So we got the terms negative 1 times negative 21 is a positive 21, plus 10 would give us a positive 31. So we have 31 of these 12,137, and then we have negative 21 of these 17,914. So hopefully you can start to see maybe the light at the end of the tunnel. We're almost getting there where we've got an expression of this, we just got to get rid of the 30,000. So that'll be our next step. This 12,000 we can get rid of. If you go back to our division algorithm statement, right, at some point we knew that 17,914, I should say 30,051 was equal to 1 times 17,913 plus this 12,137 as a remainder. So that means we can take this as 30,051 plus a negative 1 times 17,914. And then we still have the plus negative 21, 17,914. And if we collect terms, we've got and what did I think I miscopied here, right? This is 31 times this 12,000. So here we have just 31 times 3,051. Then we have a negative 31 plus a negative 21. That would give us a negative 52. And this equals 53. So what this does, this Euclidean algorithm, not only does it give us a way to find the greatest common divisor of two integers, but it allows us to express it as a linear combination. So this concludes my lecture today. I'm about to get kicked out here. I think it's pretty close to 5 o'clock. We will pick up with some more properties of the integers and the well-ordering principle. In particular, we're going to derive two forms of induction that can be derived from this well-ordering principle.